Welcome everyone in this talk series by CDSA Center for Data Science and AI. And we are really happy that Professor Romit Maulik from Penn State University is giving us a talk here. And so he holds a PhD in mechanical and aerospace engineering from Oklahoma State University. And before that, he holds an MS from the same university, and he did his bachelor's in mechanical engineering from BIMS in India. So before joining as an assistant professor, he was a computational scientist for a couple of years in mathematics and computer science division in the Argonne National Laboratory, a very prestigious one. And before that, he has been in Chicago in at different times in different roles in Argonne National Laboratory again and so on. So broadly, he works on scientific machine learning, dynamical systems, high performance computing, computational fluid dynamics, stochastic process, among others. Now, generally speaking, many of our talks have been primarily revolving around management. And here, from a technical point of view, when I first got to know about his work through our center, through some of my colleagues in my center, then I saw that he is also doing very exciting work on AI-driven models for climate, and especially working on innovative data assimilation methodology to help policy making as well. So today he will be telling us about some of his current research, and he is a very prolific researcher. Almost he has a breathtaking width. It's a great pleasure for the center to host him even, and we wanted him to be visiting us in person, but unfortunately that didn't work. But in this day and age, I guess Zoom is still a substitute, so we'll go for that. He will be telling us a lot about how to model time series from a machine learning perspective. So the floor is all yours, Romit. Thanks for giving us time. We really look forward to your talk and learn more from it.
Great. Thank you very much for the very kind introduction. Yeah, I wish I was there as well, but unfortunately, this is finals week in the US. Well, next week is finals week, so I have to deal with a lot of undergrad students who will not like it if I ditch them. So, firstly, can you see my screen?
Yeah, it's good. We can hear you
Okay,
as well.
good. All right, great. Because I cannot see you guys anymore. The way Zoom works, I can just see my screen. So, if anybody has a question, feel free to interrupt. I like to have these more informal types of talks. Yeah, thanks. Pleasure to be here. Thank you very much for the introduction. Happy to keep chatting about these and other ideas if they interest you beyond this webinar, right? So feel free to reach out, and always looking to talk to collaborators and other folks. Okay, so I'm going to be speaking today about a little bit of work I've been doing. It's among the various studies that I do that is slightly more general purpose as against, say, my classical training, which is high performance computing, for machine learning, for engineering applications, for applications that require the solution of differential equations. So I think this is a good, hopefully a good fit for today's audience. But at any time, again, if anybody has any questions, feel free to interrupt and feel free to ask me. I'm going to go through things quite in a high level detail. So if there's people who are quite say familiar with this topic, so feel free to interrupt me if you need more detail or more clarifications at any time. So this is work with an intern that I have been working with off and on. His name is San Lin. He's a PhD student in mathematics at the University of Houston. He was a Givens Fellow at Argonne National Laboratory last year, and decided to continue with me and sort of execute this nice little project. In addition, this work is collaborative with Professor Gianmarco Mengaldo, who is at the Department of Mechanical Engineering at the National University of Singapore. So, and thank you to them for really helping with this. Okay. All right, so let me start by very briefly introducing the types of systems that I study, right? And this is not just for today's talk, but for probably all of my talks. I work with dynamical systems. Dynamical systems are, as the name suggests, systems that change with time. And typically, the modeling of dynamical systems is something that is of tremendous importance uh, to society. So, for example, if you wish to make forecasts of the weather, if you wish to forecast the load that should be supported by your national power grid, uh, forecast how financial indices should behave. These are problems that are typically modeled using equations of the form that you see over here, where you have the rate of change of some quantity of interest, x, defined as a function of the quantity of interest. Frequently, the function over here can also have time in it, but for large variety of very interesting systems, you can have the right hand side look like just the system effects. These are called autonomous types of systems, right? What is done typically for, I would say, 90 to 95% of science applications out there that involve, for example, predicting X over time, is that you employ numerical methods or high performance computing, or in what laymen use, simulations to solve these systems of equations. So if people remember the techniques you learned in, say, undergraduate calculus or undergraduate numerical methods, they probably tell you how to solve such systems. Of course, you dial them up uh, a lot. So for example, x becomes a vector that has millions, maybe billions of degrees of freedom, such as the weather, right? Which has which is a very complex, high dimensional system, and then you build forecasts of this, right? So given my initial condition for x, how will x behave in the future? And this, provided you have a nice model for f over here, you can use this for a variety of applications. Now, because this is such an important task, the simulation of dynamical systems in itself is an industry, just like the dynamical systems that they wish to simulate are. For example, I really work a lot in the United States with a variety of agencies who work on weather products. So, for example, the GFS, or the Global Forecast System, is currently a product, or a simulation that is run every day by NOAA, which is the National Oceanic and Atmospheric Administration in the U.S. For forecasting the weather. So there are several such models like this spread out across the world. India has its own system as well. I could not get details about the Indian system, but I did get details about the system used in the US. And you can see the system relies on two dedicated supercomputers that are present at two ends of the continent, mainly for if there is a catastrophic weather event on one, that the US is still able to make forecasts for the weather with the other. And these are the 49th and the 50th largest supercomputers in the world, and they're dedicated solely to predicting the weather. And so, as you can see, of course, these are all technical details, but these consume a lot of power, and they take time as well to make a weather forecast. So, for example, uh, using these two supercomputers working in conjunction to make a 5-day forecast takes 2 hours, of course. Uh, but if you look at the amount of power that you need, which loosely can be correlated with the number of calculations, you're looking at 10 quadrillion calculations to run one model for 5 days, right? And so, so you can see it's something people invest a lot in. And as you can imagine, now with us living in this digital age, there's a lot of interest in actually replacing these forecasts, or augmenting them, or complementing them with data science, right? So, for example, the world's premier weather forecasting service is the ECMWF. So that's the European Center for Medium Range Weather Forecasting. The reason I call it premier is because there is this sort of an informal sort of competition between different countries on who makes the most accurate global forecast. So just to give you an example, even though this model is run by the US, it is a weather model that is run for the entire world. It is run for the entire planet. So Europe runs its model for the entire planet. The Chinese do so, the Australians do so, the Indians do so, and at this moment, and for the last few years, in in this race for being more accurate, the European Weather Forecasting Service is #1. So we in the US have a sort of a task, a grand challenge, so to speak, to actually beat them, and that's somewhat that's what motivates us. As you can imagine, forecasting the weather a little more accurately is a great strategic benefit. So so if you actually go to the ECMW website and go to, they have these charts that they release. So these weather agencies do not release the equations that they use, because that is of course a a trade secret, but they do release their forecasts, which anybody can use. If you go to these forecasts that the ECMWF are delivering, you will see now that they are actually using machine learning models to make forecasts in addition to their other equation-based forecasts. And if you this slide is slightly old, but if you look at the chart now, you will see 3 different models in there. One of these is called ForecastNet, which is a model produced by NVIDIA for weather forecasting. You have another model produced by Huawei, which is a Chinese company. It's called Pangu Weather. There's another model right now up there called GraphCast by Google. And I'm happy to speak that we are going to be releasing another model here with the Department of Energy, where I work with, which is going to be on the archive soon, where we'll use a transformer-based model, which will give us actually we will end up outperforming all of these guys. So we'll have a result that brings the US to the top for machine learning based weather forecasting, at least. So that could be the topic of another talk, but you can see it's a very exciting ecosystem at the moment, at least when it comes to weather forecasting. But in addition, there are several science applications where data is exciting a lot of people. Another project that I work on that funds some of my effort and my grad students over here is something related to nuclear fusion. There's this a very tired joke out there that nuclear fusion is always coming soon, and we're always on the brink of revolutionizing free and clean power. Unfortunately, we're still not there yet, but in recent times there has been a lot of interest in how you can potentially control the behavior of nuclear fusion reactors, such as tokamaks, as the one you see over here. This is an image of the I believe it's an image of the ITER reactor in France, using machine learning algorithms. In particular, this is very connected to the content of my talk today, uh, because one of the main limitations of nuclear fusion today is the fact that you have these events called disruptive events. Disruptive events in nuclear fusion imply when the reactor essentially starts to melt. In a nutshell, you have a sudden sort of loss of containment so the magnetic field in the nuclear reactor, it weakens, the plasma hits the wall, you have to shut down the reactor because it'll melt otherwise, right? And unfortunately, we cannot detect when this will happen. In fact, that's another grand challenge problem for the Department of Energy over here, where can you actually use any algorithm? It doesn't have to be data based; it could be equation based, to tell the operators of a nuclear reactor, nuclear fusion reactor, that okay, and a disruption event is going to happen, take corrective action ahead of time, right? So this is, and that's why this paper over here actually used a deep learning algorithm to predict these instabilities, and got themselves a Nature paper. So this was by folks at Princeton Plasma Physics Laboratories. Very exciting times to live in if you work at the intersection of dynamical systems and data. And so in today's talk, I will be focusing on a feature that you frequently observe in dynamical systems, which kind of is somewhat connected to the previous slide, but really kind of highlights the trouble with using the classical methods for prediction. When I say classical methods, I mean if I go back to this equation, I prescribe f over here based on some governing law, for example, Newton's laws, for example, quantum mechanics, and then use numerical methods to solve it. If I don't know my laws very well, which unfortunately in a vast majority of systems out there, I don't know these laws very well, I actually end up not capturing, or we actually end up not capturing a lot of very interesting and very critical behavior. To give you an example, I moved to the US in 2013, and in the winter of 2013, we had this phenomena called the polar vortex elongation. I don't know how many people are familiar with this, but what happens in the winter in the northern hemisphere is that you see this. If you can see my pointer, you have this light blue region over here. There is something called the North Atlantic jet stream over here, which is a fast moving sort of river of air, so to speak, that bounds very cold air in the northern hemisphere, right? So this air, this dark purple region is very cold air. The reason it's cold is because as you can imagine, in the winter in the northern hemispheres, you don't get sunlight in this area, so it's cold. This volume of fluid is, but the nice thing is this North Atlantic jet stream actually keeps this this sort of volume of cold air in place. Now with climate change recently, what we've observed is that this jet stream tends to weaken now and then. And when it weakens, you have these elongations of the polar vortex where the cold air goes way, way, way deeper into the north, into for example, continental US. It may also happen that it does so in Northern Europe, which has mild winters typically. And then when this happens, you end up having, your beaches frozen over in Florida, right? People don't want that in the winter. So, but unfortunately, this type of behavior is virtually impossible to predict using the current state-of-the-art models. So, one aspect of my research that I'd like to develop, and I'm making some trends in, is how do you actually capture these intermittent phenomena that are a feature of your system? This is the real world, so this is the real system. This is not something I'm hypothesizing. This is actually happening, but I'm not able to predict it, right? And so that brings me to the topic of my talk, which is, how can we use AI or machine learning for, the real-time detection of anomalies in dynamical systems? Now, of course, I gave you a lot of motivations in doing so by looking at, sort of these old-fashioned and, like outstanding grand challenge type of problem systems, but this shows up in many, many domains. And I'm quite certain that in whatever fields you work with in the audience, you would, if you work with dynamical systems, you will come across these sort of intermittent phenomena. And my experience with working with domain scientists with their systems and their intermittent phenomena is that it's just something that they bite the bullet for, and I hope to make that slightly different. Okay, so the challenges of doing such detection with any sort of method really kind of boil down to these four over here. The challenges are that these methods are these systems are very high dimensional. So if you think about something like this system, if you place a point on the planet for every latitude and longitude, then you have 180 by 360 points, because you have 180 degrees latitude, 360 degrees longitude. And so you can multiply those and you see that's a very high degree of freedom. frequently you'd want your forecast to be even finer than that. You might want it every 10th of a latitude and a longitude. That makes it, you multiply that number by 100. And so so this makes it difficult for us to, from a hardware standpoint or from an algorithm standpoint, because we're very high dimensional, right? Uh, there's unknown physics. I call it physics over here, but basically what I'm trying to represent over here is that there's unknown knowledge. In that equation I showed you in the first slide, where we had an f on the right hand side, we do not really know f appropriately. What we know about f is actually harming us at the moment, because we are not able to capture these types of systems. So we would like to avoid the use of specific equations unless we are very, very sure that these equations are correct. We want our methods to, of course, be efficient. To give you an example, if I'm trying to forecast an extreme event in any system, I can't make the forecast after that event has happened. I want this to be sufficiently ahead of time so that I can take corrective action. And finally, I want to know what's causing these events, right? And the reason I have causality in red over here is because in this talk, I will not be bringing causality into the picture. So red, because we in my group haven't been able to solve this problem yet, but we're looking into it, okay? But ideally, these are the main challenges. Okay, so now I have to apologize in advance over here. I probably got you very excited by looking at all of these very cool types of dynamics in the previous slides. But we we work using the scientific method, which means we have to start small, make hypotheses, back up these hypotheses, go back and fine tune. So we will be looking at representative systems, but things that we can still work on in a sort of like a reasonable manner for testing our ideas. And there's several canonical dynamical systems out there that are used for academic research, which are closely related to what actually happens in for example systems like the weather or in magnetic fusion. But the advantage is I can do these simulations on a laptop, so there's some ground truth that I can actually check with. Okay, so I have a list of these sort of, you can almost call these benchmark systems over here, and I'll be focusing on 3 of them. So the first, and as you can see in all these systems, I do have in some sense my dx by dt equals f of x, right? So I have a rate of change of a certain quantity that is given by something on the right hand side. So in some sense I'm cheating, right? I know what the truth is, but I hope that by having access to the truth and having access to the true intermittent behavior of the system, I can actually design algorithms that work across different applications. Okay. All right, so let me briefly introduce these systems. So the first system is the Lorentz 63 system. So I cannot see people's face over here, but I'm curious how many people know about Lorentz or any of these systems really. The Lorentz system is famous because it is essentially a 3-dimensional system. So you have x, y, and z, three components of a state, which were introduced in the 60s by Edward Lorenz, who was a climate scientist at MIT. And the reason the system is famous is because it bears the characteristics of chaos, so deterministic chaos. There's a funny story over here where the manner in which chaos was discovered by Professor Lorenz, he would run simulations for this system on a old computer with punch cards, and the output of these simulations was of course not on any terminal screen. It would come out on paper, which would be printed out, and the paper to save the amount of paper that was being printed out, he would truncate the decimal representation of x. So if x is 2.9875, he would write it as 2.98, right? This is just rounding off, or 2.99 rather. And he noticed that based on how he was rounding off x, y, and z, you would end up getting completely different results the next day. So that was how chaos was discovered. Basically perturbing the system by rounding off the representation in the decimal places was causing a completely different forecast, right? So that's how why this system is famous, and people still study it for studying chaos, right? It's a very the second system that I work with is the Rossler system. So the Rossler system is also a similar type of dynamical system, which shares some common characteristics with Lorentz. We'll go into it in the detail. And finally, I have a prototypical system that works somewhat like the weather, which is called the Kolmogorov flow. The difference between this and these other two systems is that this is a partial differential equation. These are ordinary differential equations. These become, partial differential equations are frequently very high dimensional. So for example, U over here is 64 into 64. So it's, or sorry, 32 into 32. So that's much higher than these three-dimensional systems. Please stop me at any moment if there's any questions. Okay. Okay, so let's look at Lorentz 63 and what constitutes an intermittent event for Lorentz 63, right? So if you are to then pick up this system, plug it into Python or whatever language that you like simulating with, and actually implement it to numerically solve it, you will see that as you plot the coordinates x, y, and z in phase space. So phase space is basically plotting this in a volume. You end up getting this butterfly attractor, right? This is a famous picture. And as your system moves in this volume, you will see that it almost randomly decides to move from one wing of the butterfly to the other, right? So you will start at a particular location. Anywhere you start in this 3D space will end up on one of these wings, but you keep moving from one wing to the other in a very, very difficult manner to predict. In fact, it is almost impossible to predict when you will start moving from one wing to the other. So that is the definition of an intermittent event, right? You can't really predict when this will happen. We would like to. Okay. When we do a similar visualization for Rossler, which is the second system we're looking at, you will see that it does have a similar behavior. If you plot this system in a phase or in a box, you see that the system is predominantly limited to the XY plane. So you will keep rotating over here. So you start at a particular point, you evolve X, Y, and Z, and you will see that only your X and Y change, your Z doesn't change. But for certain combinations of X and Y, you end up going into the Z plane, or you're going perpendicular to the Z plane, and then coming back down to the original place you started. Now, what is interesting is that even though this particular system is similar to what you see over here, in that there is this sort of like a nice sort of butterfly type of shape in phase space, this behavior is not intermittent, right? So this behavior is actually predictable. So if you go into for example, if you plot a one of these trajectories and you keep moving, if you see where my pointer is, if you keep moving on there, you can actually predict very accurately that you are going to go up into the third dimension and then come back down. Whereas over here, you can potentially stay on this for a very long time and then suddenly move to the other wing, right? So that's why these two systems are interesting to look at, because you can kind of compare and contrast with each other. All right. Finally, I'll quickly go over the Kolmogorov flow system. So now this is very different from the first two systems. Firstly, because it's a high-dimensional system. So you have a 32 by 32 degree of freedom. So I can't really make plots like these ones, because humans cannot visualize anything beyond a three-dimensional space, right? But what you can visualize in the system is what I'm plotting over here is something called vorticity, which is, you can think of it as the curl of a velocity. So the curl is I'm assuming you know what the curl is. If you don't know what the curl is, but you can look at these contours and actually imagine them to be regions of high circulation. So if you think about hurricanes, for example, these are hurricanes in a flow field in an idealized sort of weather. And you can see these regions of circulation, they move in a particular manner. So for example, there'll be, let me see if I can start from the scratch. So they'll be moving in a particular direction, so right to left, and then suddenly something will happen to them. It's going crazy right now, and then it moves from left to right again. If you were able to notice that, right? Then something crazy happens again, and then it starts moving right to left, right? So this craziness that happens, the sudden sort of adjustment of the positions of these circulations and then back to a sort of a predictable behavior of movement is again an intermittent behavior. So if you are actually looking at, for example, the energy of this particular flow field, which is just the square of the velocities at these individual points, you'll see that the energy shows these random crazy sort of oscillations, and then it settles into a nice sort of uh, you know a nice sort of low value, and then randomly you might have another spike, and then you have a low value. So our goal is, can we detect when these are happening, right? Because this is something that is our intermittent phenomena. Okay. Uh, of course, this is much more difficult to do, because now I don't have something in a mere three-dimensional space. I have something that is 32 by 32, right? And that begins to become a more realistic system than what I had previously. Okay. All right. So what do I use, or what in this particular talk to model these systems, to model the change point of these systems more accurately, is essentially Bayesian statistics. So the idea over here is that the weather is happening in real time. These systems are actually evolving in real time. We have a sequence of observed points, x over here. These points can potentially be high dimensional. And based on these points and some prior knowledge of when or how these change points occur, by change point I mean these intermittent events, we can, if we come up with a likelihood in the Bayesian sense for whether a certain point is a change point or not, then we can merely rely on a Bayesian update rule to flag when a particular point is in time is actually a change point. So this is our classic posterior being proportional to the prior multiplied by the likelihood, right? So in this particular setting, what we need to do is observe the true system, but not all of it. Some fraction of it is fine. If we have a model for whether this observation is it really detecting, is it really coming from a change point or not? What is the probability that it is actually because of a change point? If you have a model for that, then we can integrate it into this sort of recursive type of relation to in real time flag us whether something has a high probability of being a change point or not, right? So in practice, what we use in Bayesian online change point detection is a slack or a latent variable called the run length, R, over here. So the R is basically a quantity that tells us.
Romit, can I ask
Yeah,
you a question here?
please go ahead.
So this, I mean, it seemed like the current topic is kind of a switch from the previous one, in the sense that all the previous systems that you described, for example, the Rossler and so on, they are all,
Yes.
I mean, I can be wrong here, but they are all deterministic in nature. And if
Yes,
they are
yes.
perturbed, then the dynamics would be very different. So all the simulations
Mhm.
that you had shown was for an unperturbed system. But here you are introducing perturbation, and the idea of applying Bayesian algorithms would be that these are fundamentally stochastic. And so basically, my point, I suppose, is that chaotic systems and stochastic systems are philosophically different.
I absolutely agree. I
So
absolutely agree.
what is the, I mean, connection here from the previous bunch of models to this one?
So the connection here is that we're not defining that the system is stochastic. We're defining that the arrival of a change point is stochastic. Does that make sense? So there
No,
is a
that makes
probability.
sense. But why? I mean, in that case, why not just? I mean, I'm just being devil's advocate here. Then why not just start from this model to begin with? Why refer to chaotic systems to begin, at all?
So the chaotic systems, those are mainly for generating data. We're not going to be using equations anymore. We're going to be using observations from those systems to fit these models. So
Is the underlying assumption that the eventual dynamics that you will be wherever you'll be getting your data from, that is fundamentally a chaotic dynamics that you are aware of, but they
yes,
are also subject to these TCs, which are these kind of
change points.
shocks that are affecting them. I see.
Yes. So the dynamics can be, deterministic, but or deterministic chaos to be precise. But the events that characterize these sudden changes in the system are probabilistic in nature. So, for example, if I have a system that starts at a particular initial condition over here, uh, even though I deterministically evolve the system, it is so sensitive to the initial conditions that as there is no way for me to predict when it will start switching from one side to the other. So that can be actually modeled as a almost like a random variable.
Okay,
Whether
I see. All right. Okay. Okay.
you see,
Yeah, this is good.
yeah.
Yeah.
So that's okay. So uh, deterministic chaos, it does cause people to scratch heads. Because because the the name itself is somewhat like a oxymoron, right? You have determinism in there and then chaos in there as well. So and that is why it is such a cool thing to study. So yeah. So thank you for the question. This is that actually it's a very perceptive question. What we wish to do over here is we do not say that like um, um, uh, there is a probabilistic model for how the state is evolving. We merely say that there is a probabilistic model for a uh, whether a timestamp is actually due to a change point, or whether a particular timestamp is a change point. So for example, P of xi given tc can be assumed to be probabilistic, and whether a particular timestamp is a change point can also be assumed to be probabilistic. Okay, so how does this work in practice? So if you do have a model that falls into this particular sort of uh, category, you're ready to go. You can go in there and perform a Bayesian statistic update as you want. But the issue with this is Bayesian statistics is computationally expensive. In practice, if you don't know what your P is exactly, then this particular computation requires something like Markov chain Monte Carlo, some sort of sampling, which then starts eating away at the gains of using data-driven modeling, right? Because if you have to do sampling from a very high dimensional density, remember this the size of the random variables can be very high. Then you may you lose the gains of using data. So what Bayesian online change point detection does is it simplifies the problem by using the slack variable, these variables called the run length. So the run length over here is basically almost intellectually simplifying the problem even further by saying that perhaps I can actually introduce a variable that captures how long it's been since I last had a change point, right? So R over here, if R is 0, that means I am at a change point right now. If R is 1, that means I had a change point at the previous time step. If R is 10, I had a change point 10 time steps ago, right? And so the idea is, if you can quantify this probability, right, this joint probability of R and all the data that you've observed, I can see, I can capture when, what the probability is that I had a change point in the past, and what the probability is that I am going to have a change point at this current time step. And so if you just do a like a decomposition of this particular density using the marginal law of probabilities, these are details, you will end up with a recursive relation over here, where you say that this joint probability between R and the state at all the previous time steps is recursively updated based on the same probability at the end of the previous time step. So this is the online nature of this algorithm. So you're only ever tracking this particular quantity over here. You observe some new data at T, and based on, again, a model that you have for these two quantities, right, which I'll introduce in a bit, you then update your joint probability density of your run.
Robbie,
Okay.
there is a
Yes.
query on
Yes.
the chat box which says that
Mhm.
how a change point in data in weather would look like.
So that's a great question. It really depends on what you're looking for, right? So I gave you the example of an extreme cold snap, which comes from the weakening of the jet stream. It could be something like a extreme heat wave. It could be something like which is far more difficult to predict. It could be something like an extreme precipitation event, right? All of these are very important for downstream infrastructure. If you remember, there was these ice storms in Texas a couple of years ago, which crashed the Texas power grid. So Texas has a different power grid from the rest of the country. And so if you want to harden infrastructure to, for example, climate change, there would be different variables to look at. So what is typically the most difficult to predict are things like heat waves, wildfires, and precipitation events. So flash flooding, for example, right?
I see. And
So
two follow-up questions are, what is the time unit here, and how many variables you're keeping track of?
okay, so the time unit over here is up to you, really, right? So in some sense, the weather is not discrete. The weather is a continuous type of unit, but forecasts are made, for example, every hour, right, or every half an hour. So you can think of that as half an hour if that is the resolution you want, right? So, but if the resolution you want is on the order of days, then you can set that as your time unit. So it's really, the question really boils down to the end user, right? And what was the second question again? Sorry.
How many variables you are keeping track of, dimensionality of
Okay,
them.
this is dependent on the on the problem again, right? So I'll have three sets of results for you, time permitting, and based on these three sets of results, you'll have different numbers of variables. So for the Lorentz system, you have just three, so three scalars. For the Rossler, you also have three scalars. For the Kolmogorov flow, you have 32 by 32 scalars. So it's an image of 32 by 32. But you will see one of our contributions was to actually compress this high dimensional quantity by using deep learning, because if the state is very high dimensional, if the number of degrees of freedom is very high, this online update slows down a lot. We'll get into that. Okay.
So you have around 15 minutes from now.
Yes, that's perfect. Okay, so we have this sort of Bayesian statistic to kind of recursively update our density for the run length given the history of a particular variable. There are some choices that we have to make for modeling. This is now where science in some sense becomes art, where we have to find a model for example the conditional run length based on the run length of the previous time step. We use something called the hazard function over here. The reason we do this is you know mainly because of computational ease, ease to model, and there's a lot of research going on into better designing these things. So this is not, in some sense, my job. We mainly looked at using Bayesian statistics in their most efficient form. But for example, a computational probability researcher would probably go into designing these things more accurately. Uh, So this was our model for the run length. What is interesting is the model for a lot of equations over here. No need to get scared. This what is most interesting here is the model for which we call the likelihood or the predictive distribution, which is the probability of a particular type of observation given the run length and the past observations. So over here, what we need is a model which for a density which is updated in real time, right? So again, this goes back to my previous discussion about Bayesian statistics. If you do want to have a new posterior distribution, given that you have observed some data, if you leave these distributions to be arbitrary, then you have to calculate this high dimensional integral, which is not an option at all because we want to do this in real time. So in this particular study, we use a conjugate distribution. So again, if you're familiar with Bayesian statistics, conjugate distributions are those where the posterior is the same form as the prior, and as you observe data, you can update just the hyperparameters of the distribution. So you can think of, for example, the Gaussian distribution to be an example of a conjugate distribution, where as you observe new data, the mean changes or the variance changes. Very easy to kind of put it. So we generalize the Gaussian. So what we have over here is an exponential distribution, which is like a superset of Gaussian type distributions, where the nu over here is kind of like the mean, and the chi over here is kind of like the uh, um, the covariance, right? And so we observe new data, we change this particular probability over here, and then we update our model. Okay. All right, so this is the overall algorithm. This again may look complicated, but I promise you this is just the maybe 100-ish lines of code in Python. So and the reference, oh, unfortunately I forgot to put the reference over here, but this is McKay and Adams paper on Bayesian online change point detection. This is referred to in my paper for sure, right? And so the idea of here is that you initialize a prior density for the change point. Either you set it at 0 or you set it using some logic based on your historical data, and some prior hyperparameters for this distribution over here, the predictive distribution. You observe new data based on the models that you set up for these distributions. You update them. You update them recursively for different run lengths. So the idea is that for each value of run length over here, RT, you will have a different probability. So it's almost like a lookup table, really. And then based on that probability, what you want to do is you want to set a threshold. So what that means is, if, for example, the probability of a certain run length is highest, it will tell you that that is, you can select that as the last time you had a change point. And so, for example, if my probability of run length being 0 becomes highest, it means that you have experienced a change point, right? So, and that is basically how we use this. If P of RT equals 0 is highest, we say that we have experienced a change point. All right, so now, before going into results, I really quickly want to talk about the curse of dimensionality, right? So with large, high dimensional systems, this distribution no longer becomes a matter of estimating means and variances or standard deviations. It becomes an issue of estimating what the mean and the matrix covariance is, which then becomes very, very large because the matrix is n by n if you have n degrees of freedom. And so in this particular study, we want to compress our system in such a way. So for example, our Kolmogorov flow example was 32 by 32. We want to bring it down to something reasonable in such a way that we still have to estimate a mean and a variance for a lower degree of freedom system. And in particular, we don't want to estimate matrices. We still want to deal with vectors. So we also want to use a beta variational autoencoder. So for people who are not familiar, this is a deep learning architecture that compresses your data. So you give it an image and you find a low dimensional space that is much more reduced in dimensionality than the original space. but the compression happens in such a way that you can reconstruct the original space quite accurately. What is peculiar about this particular type of architecture is that the latent space leads to a decorrelation in the off-diagonal component. So if you look at the Z over here, which is, let's say, 4-dimensional compared to 32 by 32 in the original space, then if you build a 4x4 correlation matrix for all the data points that you have in the latent space, you will see that it will be diagonally dominant, right? So it will be high values in the diagonals for correlations, which makes sense, and very, very low values in the cross off diagonals. And this, as you will see, accelerates our process of change point detection dramatically. Okay, so let's look at some results, right? So if you take the Lorentz system and then do this change point detection algorithm for the Lorentz system with, for example, using the beta VAE, but not to reduce dimensionality. So our original space and the latent space here is still 3-dimensional. It's just that there is no correlation across the 3 components because of this, this effect of the beta variational autoencoder. You see that we are able to, firstly, let me explain this plot over here. There is a mislabeling of this plot because of my grad student, but this is not Rossler, this is Lorentz. The green lines over here, the dark green lines are change points. And so every time there's a change point, I say that we have moved from a green region to a white region and back and forth, right? And if you actually plot the change points in the phase space, you will see these are the red points. We get an interesting type of behavior where we are predominantly able to detect this region of transition between one wing of the attractor to the other. We also pick up a few spurious other locations, and here again, this is where science becomes art. This is a probabilistic model, so sometimes you're going to be off. So we are working on doing some hyperparameter tuning to make this more robust. But all in all, I would say that this is a good sort of preliminary proof of concept result where we're able to actually detect when our system has begun the process of moving. Now you may say, oh, this is obvious, right? I can just visually look at it and say that I'm about to move. You're right. Yes, it is obvious, but what's obvious in a 3-dimensional space is not really obvious in a very high dimensional space. So this is in some sense a sanity check that our model actually works well. Okay. Now the second system that again we want to use for a sanity check is the Rossler system. And what is peculiar about the Rossler system, like I said, is that the movement from these 2 wings of my dynamics from one wing to the other is not an intermittent event. It is a very predictable type of event. And as you can see, our change point detection algorithm does not actually detect change points as you move from one wing to the other. The one green line that you see over here is an experiment that we ran where we ran the Rossler system for 500 time units and then changed a parameter. So if you remember the Rossler system way back at the top had these parameters over here, the gamma, the lambda, and the chi. So if you change one of these parameters abruptly, the system changes, right? The behavior of the system does not. The only thing that changes is how high it goes into the 3rd dimension. It's able to pick up that you've changed this parameter, but it does not flag movement off the 2D plane, which is very nice because it's telling us that it's not merely predicting a movement into a different wing of the attractor. It is actually detecting an intermittent event. So this was and I have to thank the reviewers in my paper for suggesting this, because they were like, maybe it's just learning to move to a new region of phase space. So they asked me to check for Rossler, and I was very happy that the method was actually also was not detecting change points in Rossler, because there are no change points. Okay, finally, the Kolmogorov flow. So over here, again, our system is 32 by 32. I'm going to speed up a little now. I want to reduce it to 4 by 4 because I do not want to spend a lot of computation and computing the means and covariances of these 32 by 32 systems. We use the autoencoder to compress this to a 4-dimensional latent space, but as you can see, we are able to qualitatively, and in the paper we have more quantitative numbers, we are able to qualitatively reconstruct the behavior of this system even in using just 4 latent space variables. And what is nice over here is that if you look at the correlation matrix in that 4-dimensional space, you can see we're not able to eliminate correlations in the off-diagonal components, but you can see it is definitely very diagonally dominant. So now that we have a 4-dimensional sort of system, let's perform our change point detection. I'm going to skip this slide for time and just look at that energy quantity I introduced when I was introducing the Kolmogorov flow system. So actually, let me go back to this slide and spend a little time on this. So over here, the quantity I'm plotting is basically this latent space variable z, which is just 4-dimensional, and then showing this to my BOCD algorithm to actually predict when change points are happening. So the green dashed lines are when change points are happening. This triangular map is actually plotting the run length probability. So as you can see, the run length probability for a certain quantity is high, and then it drops down to 0. So we end up having a change point. And again, the nice thing about the system is that it may be a high-dimensional system, but it has been studied for a long time. And so this was a case where we bonded with some chemical engineers who have been studying the system for various different applications, where they've actually used a physics-based algorithm to computing these change points. What they do is they look at this energy quantity, like I suggested, and they have a very complicated, I won't go into the details, but it's in this reference where they have this very complicated physics-based, first principles-based method to detect when a particular intermittent event is happening. And I was happy to say that that's the red line over here, which they prescribed. And so when I got the data from them, I said, okay, let us see how our Bayesian method works. And as you can see, despite having no knowledge of the system, other than observations of the state, we are able to detect in real time that these events are happening. Now, you may again say that, okay, if I have access to this quantity of interest, this energy, I can visually make this determination. I say, absolutely, you're right. You can visually make this determination. But again, what we are able to do is we are actually able to show it this high-dimensional flow field and have it detect this particular behavior, which is very promising for real-world applications where it isn't possible to distill your observations down to a very convenient metric like this, right? So that's something that I think that we are quite excited about. Okay, I might be over time, but I'm going to just quickly show you this table, which shows that the use of the beta variational autoencoder does accelerate the change point detection algorithm. If you were to use your original model without actually compressing the state, you would get orders of magnitude more cost in computing these change points, which start to kind of affect our the utility of our tool. But we are able to keep this quite nice and compact and nice and fast based on these beta variational arguments that we had. And finally, I will stop here and conclude, by basically highlighting what we have not done. We have not extracted causal mechanisms. Okay, so we've just come up with a method to detect when these will happen, and we have also not sort of explored all we can do with the type of distribution that we can use. So I've used very simple distributions for this online update, but in practice, perhaps these are not the best choices, right? So there's a lot more work to be done, and it's exciting times, right? Okay, so I want to acknowledge, of course, Sen, who did most of the work over here. As he was a phenomenal intern with me, and he continues to push on these ideas. And of course, collaboration with Gianmarco, funding, of course, from various agencies. And I will thank you over here, and again, happily welcome any feedback or collaborations or follow-ups. Thanks a lot for the invitation, and it's been a pleasure.
Thanks, Romit. This is a fantastic talk.
Sure.
So we are kind of out of time, but there are two questions. If you can kindly take them up, it would be useful. So the first
Sure.
one is, in the data, do you allow for any kind of seasonality, which I suspect not the case
Yeah,
currently.
we detrend the data.
Yeah.
So we use the standard, best practices of time series analysis for pre-processing the data to make sure there's no biases or no false flag sort of detections. Yeah.
And the second question, I guess, is a follow-up from your answer here, which asks if if it is ex post or ex ante, in the sense that does it detect that the change points have already happened, or does it kind of predict whether it's going to happen?
So prediction is a completely different problem altogether. It's a much harder problem, right? So what we are doing is we are observing some fraction of the truth in real time, and we are flagging if a change point has happened or not. To flag that a change point happens, let's say several time units in advance, you then run afoul of Mother Nature, because in some sense these systems are mysterious. And if they were so easy to predict, if these change points were easy to predict, we would be predicting them ahead of time. So at the moment, of course, people are trying to maximize the predictability of these change points, but what we really have at the moment is probabilistic models, right? And real-time detection. So our problems are similar, but I'm doing something a little more conservative. I'm saying, okay, I don't want to predict ahead of time, but at least when it's happening, can I predict it rapidly, right? So to give you a very contrived example, let's say you are in Florida in the US, which is a warm place in the winter, right? You may have occasional days when it starts to get cooler, but is that because of a extreme event, or is that because of a regular sort of cold day in the winter, right? So it's still valuable to have these being predicted in real time.
Thanks, Romit.
Yes,
So, and thanks
it was a pleasure.
attendees for posing some useful questions, and I think there is a lot of learning for all of us here. So, Romit, we will be in touch, and next time you are in India, we would be very happy if you can possibly visit us.
Oh,
And
I really appreciate the invite. I wish I was there.
and
This winter's travel got a little messed up.
yeah, absolutely.
So yeah.
All right. Thank you. Thanks, everyone.
Thanks.
Bye.
See you around.